What's up, YouTube? It is day 39 on the Road to Code, 100 Days of Code Challenge. So, finished up with the basic structure, data structures, and as I said in the last vlog, that I read an article, or a blog rather, about data structures, explaining the bigger picture, and that I'd be reading it for this vlog. So that's what we're gonna do. So this is gonna be a little bit of a longer format here. So let's just get right into it. Introduction. As business logic moves from the back to front, more and more expertise in front-end engineering becomes even more crucial. As front-end engineers, we depend on view libraries like React to be productive. View libraries in turn depend on state libraries like Redux to manage the data. Together, React and Redux subscribe to the reactive programming paradigm in which UI updates react to data changes. Increasingly, backends act simply as API servers, providing endpoints only to retrieve and update the data. In effect, the backend just forwards the database to the front end, expecting the front end engineer to handle all of the controller logic. The raising popularity of microservices and GraphQL attests to this growing trend. So this is a little bit more advanced than where we're at right now, talking about React and Redux, the JavaScript libraries that we'll begin into in the next course of Free Code Camp. Now, in addition to having an aesthetic understanding of HTML and CSS, front-end engineers are expected to master JavaScript as well, as data stores on the client become replicas of databases on the server. Intimate knowledge of idiomatic data structures become pivotal. In fact, an engineer's level of experience can be inferred from his or her ability to distinguish when and why to use a particular data structure. Then here's a quote here: bad programmers worry about the code, good programmers worry about the data structure and the relationships. It's the creator of Linux and Git. Alright, at a high level, there are basically three types of data structures. Stacks and queues are array-like structures that differ only in how items are inserted and removed. Like linked lists, trees, and graphs are structures with nodes that keep references to other nodes. Hash tables depend on hash functions to save in local data. In terms of complexity, stacks and queues are the simplest and can be constructed from linked lists. Trees and graphs are the most complex because they extend the concept of a linked list. Hash tables need to utilize these data structures to perform reliably. In terms of efficiency, linked lists are most optimal for recording and storing data, while hash tables are most performant for searching and retrieving data. Stack, arguably the most important stack in JavaScript, is the call stack, where we push in the scope of a function whenever we execute it. Programmatically, it's just an array with two principal operations, push and pop. Push adds element to the top of the array, while pop removes from the same location. In other words, stacks follow the last in, first out protocol, LIFO. And then they show an example here. Queue. JavaScript is an event-driven programming language which makes it possible to support non-blocking operations. Internally, the browser manages only one thread to run the entire JavaScript code, using the event queue to enqueue listeners and the event loop to listen for the registered events. To support asynchronous, such a big word, asynchrony, such a big word, but I mean, I know what it's saying. In a single threaded environment, to save CPU resources and enhance the web experience, listeners functions dequeue and execute only when the call stack is empty. Promises depend on this event-driven architecture to allow a synchronous style execution and asynchronous code that does not block other operations. Programmatically, queues are just arrays with two primary operations, unshift and pop. Unshift enqueues items to the end of the array, while pop dequeues them from the beginning of the array. In other words, queues follow the first in, first out protocol, FIFO. If the direction is reversed, we can replace unshift and pop with push and shift respectively. Alright, so stacks was LIFO, which is last in, first out, and Q is first in, first out. And they just show an example here. Linked list, like arrays, linked list store data elements in sequential order instead of keeping indexes. Linked list hold pointers to other elements. The first node is called the head, while the last node is called the tail. In a singly linked list, each node has only one pointer to the next node. Here, the head is where we begin our walk down the rest of the list. In a doubly linked list, a pointer to the previous node is also kept. Therefore, we can also start from the tail and walk backwards towards the head. Linked lists have constant time insertions and deletions because we can just change the pointers. To do the same operations in arrays requires linear time because subsequent items need to be shifted over. Also, linked lists can grow as long as there's space. However, even dynamic arrays can automatically resize, could become unexpectedly expensive. Of course, there's always a trade-off. To look up or edit an element in a linked list, we must have to walk the entire length, which equates to linear time. With array indexes, however, such operations are trivial. Like arrays, linked lists can operate as stacks. It's simple as having the head be the only place insertion and removal. Linked lists can also operate as queues. This can be achieved with a doubly linked list, where insertion occurs at the tail and removal occurs at the head, or vice versa. For a large number of elements, this way of implementing queues is more performant than using arrays, because shift and unshift operators at the beginning of arrays require linear to reindex every subsequent element. Linked lists are useful in both client and server. On the client, state management libraries like Redux structure, its middleware logic is linked list fashion, where actions are dispatched. They are piped from one middleware to the next until all is visited before reaching the reducers. On the server, web frames like Express also structures middleware logic in a similar fashion. When a request is received, it is piped from one middleware to the next until a response is issued. An example of a double linked list in the code, and an example here. Next topic is a tree. A tree is like a linked list, except it keeps references to many child nodes in a hierarchical structure. In other words, each node has more than one parent. The document object model DOM is such a structure with a root HTML node that branches into the head and body nodes, which further subdivide into all of the familiar HTML tags under the hood. Prototypical inheritance and composition with React components also produce tree structures. Of course, as an in-memory representation of DOM, React's virtual DOM, same thing, is also a tree structure. The binary search tree is special because each node can have no more than two children. The left child must have a value that is smaller than or equal to its parent, while its right child must have a greater value. Reminds me of an LML multi-level marketing structure where it's two legs. If you guys are familiar with that. Structured and balanced in this way, we can search for any value in logarithmic time because we can ignore one half of the branching with each iteration. Inserting and deleting can also happen in a logarithmic time. Moreover, the smallest and largest value can easily be found in the leftmost and rightmost leaf, respectively. Traversal through the tree can happen in a vertical or horizontal procedure. In depth first traversal, DFT, in the vertical direction, a recursion algorithm is more elegant than an iterative one. Nodes can be traversed in pre-order, in order, or post-order. We need to explore the roots before inspecting the leaves. We should choose pre-order. But if we need to explore the leaves before the roots, we should choose post-order. As its name implies, in order enables us to traverse the nodes in sequential order. This property makes binary trees optimal for sorting. Alright, optimal for sorting. And breadth first traversal, BFT, in the horizontal direction and iteration approach is more elegant than a recursive one. This requires the use of queue to track all the children nodes with each iteration, the memory needed for such a queue might not be trivial. However, if the shape of the tree is wider than deep, BFT is better choice than DFT. Also, the path that BFT takes between any two nodes is the shortest one possible. Okay, so this seems to be faster iterations and execution. Graph. If a tree is free to have more than one parent, it becomes a graph. Edges that connect nodes together in a graph can be directed or undirected, weighted or unweighted. Edges that have both direction and weight are analogous to vectors. Multiple inheritance in the form of mixins and data objects that have many-to-many relationships produce graph structures. A social network and an internet itself are also graphs. The most complicated graph in the nature is our human brain, which neural networks attempt to replicate to give machines superintelligence. An example of a graph in code, another example there, and then hash tables. A hash table is a dictionary-like structure that pairs keys to values. The location of memory of each pair is determined by the hash function, which accepts a key and returns the address where the pair should be inserted and retrieved. Collisions can result in two or more keys converted to the same address. For robustness, getters and setters should anticipate these events to ensure that all data can be recovered and no data is overridden. Usually, linked lists offer the simplest solution. Having a very large table also helps. If we know our addresses will be integer sequences, we can simply use arrays to store our key value pairs. For more complex address mapping, we can use maps or objects. Hash tables have an insertion and lookup of constant time on average. Because of collisions and resizing, this negligible cost could grow in linear time. In practice, however, we can assume that hash functions are clever enough that collisions and resizing are rare and cheap. If keys represent addresses and therefore no hashing is needed, a simple object literal can suffice. Of course, there's always a trade-off. The simple correspondence between keys and values and the simple associative between keys and addresses sacrifice relationships between data. Thus, hash tables are suboptimal for storing data. If a trade-off decision favors a retrieval over storage, no other data structure can match the speed of hash tables for lookup, insertion, and deletion. It's no surprise, therefore, that it's used everywhere. From the database to the server to the client, hash tables, and in particular, hash functions, are crucial to the performance and security of the software applications. The speed of database queries relies heavily upon keeping table indexes that point to records in sorted order. This way, binary searches can be performed in this word's always a tongue twister. Logarithmic time, a huge performance win, especially for big data. On both the client and server, many popular libraries utilize memorization to maximize performance by keeping a record of the inputs and outputs in a hash table. Functions run only once for the same inputs. The popular reselect libraries uses the caching strategy to optimize map state to properties function to Redux-enabled applications. In fact, under the hood, the JavaScript engine also utilizes hash tables called heaps to store all of the variables and primitive we create. They are accessed from pointers on the call stack. The internet itself also relies on hashing algorithms to function securely. The structure of the internet is such that any computer can communicate with another computer through a web of interconnected devices. Whenever a device logs into the internet, it becomes a router through which data streams can travel. However, it's a double-edged sword. A decentralized architecture means that any device in the network can listen and tamper with the data packages that it helps to relay. Hash functions such as MD5 and SH255 play a critical role in preventing such a man-in-the-middle attacks. E-commerce over HTTPS is safe only because these hashing functions are used. Inspired by the internet, blockchain, crypto, you know what it is, technologies seek to open source the very structure of the web at the protocol level. by using hash functions to create immutable fingerprints for every block of data. Essentially, the entire database can exist openly on the web for anyone to see and contribute to. Structurally, the blockchains are singly linked list of binary trees of cryptographic hashes. The hashing is so cryptic that a database of financial transaction can be created and updated out in the open by anyone. The incredible implication is the awesome power to create money itself. What was once only possible for governments and central banks, now anyone can securely create his or her own currency. This is the key insight realized by the founder of Ethereum and the pseudo-founder of Bitcoin. I mean, I like that he mentioned blockchain, but Ethereum, comparing decentralized blockchain and putting Ethereum in there, come on, bro. But as more and more databases move into the open, the need for front-end engineers who can abstract away all the low-level cryptographic complexities will compound as well. In this future, the main differentiator will be the user experience. Conclusion: as logic moves increasingly from the server to client, the data layer on the front end becomes paramount. The proper management of this layer entails mastery of the data structures upon which logic rests. No one data structure is perfect for every situation, because optimizing for one property always equates to losing another. Some structures are more efficient at storing data, while some others are more performant for searching through them. Usually one is sacrificed for the other. At one extreme, linked lists are optimal for storage and can be made into stacks and queues, linear time. At the other, no other structure can match the search speed of hash tables, constant time. Tree structures lie somewhere in the middle, and only a graph can portray nature's most complex structure, the human brain. Having the skill set to distinguish when and articulate why is a hallmark of a rockstar engineer. And that is the end of the article. Kind of a long structure for a video, but again, doing this vlogging and blogging documentation is literally to document the process and to remember the importance of everything that I'm learning. And speaking about it and writing about it surely helps remember. And that's pretty much the update for today. As always, just like, comment, and subscribe. Check out my blog at trillamanila.com and Twitter at trillamanila as well. Peace out.